Hello there, beautiful human. It's your boy Chad, your fearless guide through the cosmic safari. I've gazed into the void, and honestly, the void blinked first. So wherever you're watching from tonight, I want you to get comfortable. Let your shoulders drop, take a slow breath, and close your eyes. Because tonight, we're going on a journey. Not a small journey, not a road trip. We're talking about the deepest, strangest, most mind-bending mystery in all of modern science. We are talking about dark energy, the invisible force that makes up more than 2/3 of everything that exists. The thing driving the entire universe apart, right now, as you lie there. Scientists have known about it for nearly 30 years, and they still don't fully understand what it is. But we're going to give it a shot, so settle in and let's begin. Now, before we dive into the deep end of the cosmic pool, let's take a moment to appreciate just how strange the universe actually is. And I mean genuinely, uncomfortably strange. The kind of strange that keeps physicists awake at night, and it does. Because here is a question that sounds simple, but turns out to be one of the most profound puzzles ever posed by human minds. What is the universe made of? You might think you know the answer. Matter, right? Atoms, molecules, stars, planets, gas clouds, the water in your glass, the blanket over your legs. Everything you can see and touch and weigh and measure. That's the universe. Except here's the part that changes everything. Everything you have ever seen, every galaxy photographed by every telescope ever built, every star and every constellation you've ever looked up at on a clear night, every planet, every moon, every asteroid drifting silently through interplanetary space, every human being who has ever lived, and every human being alive right now, all of it combined, accounts for roughly 5% of the total content of the universe. 5%. The other 95% is something else. Something we can neither see nor touch nor measure directly. Something we know exists only because of what it does to the things we can see. And that 95% is divided into two great mysteries. About 27% is something called dark matter. It's invisible. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we can currently detect. But it has gravity. And that gravity plays an enormous role in shaping the large-scale structure of the universe, holding galaxies together, pulling matter into the vast cosmic web of filaments and clusters and voids that defines the large-scale structure of everything. Dark matter is extraordinary and fascinating, and it deserves its own dedicated evening. But tonight it is not our main character. Our main character is the remaining 68%, the largest single ingredient in the universe, the thing called dark energy. And dark energy is not matter of any kind. It's not particles. It's not something with mass that you could, even in principle, weigh or collect. Dark energy, as far as we currently understand it, is a property of space itself, a kind of energy woven into the very fabric of the universe, present everywhere, constant, and its effect on the cosmos is unlike anything else we know. Dark energy is causing the universe to expand, not just expand, to accelerate, to fly apart faster and faster, with every passing moment, every passing billion years. The galaxies of the universe are being carried away from each other by the expansion of space itself, and dark energy is the engine behind that expansion. To understand why this discovery was so shocking, why it rewrote cosmology almost overnight, we need to go back to the beginning, not the beginning of the universe, though we'll get there, the beginning of our modern understanding of it. And that story begins, as so many great scientific stories do, with one man staring at equations and refusing to accept what they were telling him. The year is 1915. Albert Einstein, working in Berlin during the middle of the First World War, has just completed his general theory of relativity. It is, by almost any measure, one of the greatest intellectual achievements in human history. Where Isaac Newton, 2.5 centuries earlier, had described gravity as a force acting mysteriously across empty space, a pull between masses that he himself admitted he could not explain, Einstein reimagined gravity from the ground up. In Einstein's framework, gravity is not a force at all. It is the curvature of space-time. Mass and energy warp the fabric of space and time around them, the way a bowling ball, placed on a stretched rubber sheet, creates a depression. And other objects, moving through that warped fabric, follow curved paths. What we experience as gravity, the pull of the Earth beneath our feet, the orbit of the moon, the trajectory of a falling apple, is not a force pulling things together. It is geometry. It is the shape of space-time itself. Einstein's equations of general relativity were beautiful, compact, and extraordinarily powerful. They described not just the gravitational field around individual objects, but the behavior of space and time on the largest possible scales. They were equations that could in principle describe the universe as a whole, and when Einstein applied his own equations to the universe as a whole, he encountered something that deeply troubled him. The equations predicted that the universe could not be static. They predicted that space had to be either expanding or contracting. The universe, according to general relativity, was dynamic. It changed over time, it moved. But in 1915, almost nobody believed this. The prevailing view, shared by nearly every scientist and philosopher at the time, was that the cosmos was eternal and unchanging. It had always existed roughly as it is now. Stars might be born and die, but the grand structure of the universe itself as a whole, was permanent, fixed still. The very idea of a universe that evolved or changed on the largest scales seemed almost philosophically incoherent. Einstein looked at his equations. He looked at what they were predicting, and he decided that his equations must be wrong, or at least incomplete. So he made a modification. He inserted an additional term into his field equations, a mathematical constant that represented a kind of gentle repulsion built into empty space itself, a pressure that acted outward across all of space, exactly counterbalancing gravity's tendency to pull everything together. With this term correctly adjusted, the equations described a stable, static universe, a universe that neither expanded nor collapsed, a universe that agreed with everyone's intuitions about the cosmos being eternal and unchanging. Einstein called this term the cosmological constant, and denoted it with the Greek letter lambda. He was satisfied, for a while. Then, in 1929, everything changed. Edwin Hubble was an astronomer working at the Mount Wilson Observatory in the mountains above Pasadena, California. He had already done extraordinary work establishing that many of the fuzzy spiral and elliptical structures visible through telescopes, long debated as clouds of gas within our own galaxy, were in fact entirely separate galaxies in their own right, each containing hundreds of billions of stars at distances of millions or billions of light-years. The Milky Way, for all its grandeur, was just one of countless galaxies in a universe far vaster than anyone had imagined. But Hubble's 1929 observation was even more consequential. By combining his distance measurements with earlier measurements of how fast those galaxies appeared to be moving relative to us, derived from the Doppler shifting of their light, Hubble found something remarkable. Almost every galaxy he studied was moving away from us, and not randomly. The further a galaxy was, the faster it was receding. There was a clean linear relationship between distance and recession speed. This is now called Hubble's law, and its implication is stark and unavoidable. If every galaxy is moving away from every other galaxy, and the further ones are moving faster, then space itself is expanding. The universe is not static, it is growing. Running this expansion backward in time, all of space converges to a single unimaginably hot and dense state, a beginning, what we now call the Big Bang. Einstein reportedly visited the Mount Wilson Observatory shortly after Hubble's results became widely known. He studied the data, he acknowledged the observations were correct, and he declared, by some accounts, that the introduction of the cosmological constant had been the greatest blunder of his career. He had modified his own equations, introducing an ad hoc mathematical fix to preserve his intuition about a static universe. And that intuition had been simply wrong. The universe was dynamic, it was expanding, and the cosmological constant, as far as Einstein was concerned, was an unnecessary invention that could now be thrown away. He discarded it. He moved on. But the cosmological constant had a way of refusing to stay discarded. It would return, decades later, in circumstances Einstein never anticipated, as something not just mathematically possible, but physically necessary, something the universe appeared to actually contain. For the next several decades after Hubble's discovery, cosmologists built and refined the Big Bang model. They worked to understand the rates of expansion, the density of matter in the universe, the origin of the light elements like hydrogen and helium, the nature of the cosmic microwave background, the faint cold afterglow of the Big Bang itself, first detected in 1965 by Arno Penzias and Robert Wilson, who famously mistook it at first for pigeon droppings fouling their antenna in New Jersey. Throughout this period, the prevailing assumption about the expansion of the universe was broadly intuitive. Gravity should be slowing it down. After the Big Bang, the universe had been flung outward with enormous energy, but all that matter filling space was gravitationally attracted to all other matter. Over time, gravity should act like a brake. Expansion would continue, because the initial energy of the Big Bang was enormous, but it would gradually decelerate. The exact rate of that deceleration would depend on how much matter the universe contained. With enough matter, expansion might eventually halt and reverse, leading to a future collapse, the Big Crunch. With less matter, expansion would continue forever, growing ever slower but never quite stopping. What nobody anticipated was that expansion might be doing the opposite of decelerating. To measure the history of cosmic expansion, astronomers in the 1990s turned to a remarkable tool, a specific type of stellar explosion called a Type 1a supernova. To appreciate why these explosions are so useful, you need to understand what causes them. Imagine a binary star system, two stars orbiting each other. One of them has exhausted its nuclear fuel and collapsed into what's called a white dwarf. A white dwarf is the dense, hot remnant of a dead star. It's roughly the mass of the Sun compressed into a sphere about the size of the Earth. It's no longer fusing nuclear fuel. It's supported purely by the quantum mechanical resistance of electrons being squeezed too closely together, a phenomenon called electron degeneracy pressure. If the white dwarf has a companion star close enough, it can draw material from that companion, gas streams from the living star onto the white dwarf's surface. The white dwarf gains mass, and here is the key detail. There is a hard physical limit to how massive a white dwarf can become before electron degeneracy pressure can no longer support it. This limit, about 1.4 times the mass of our Sun, was calculated in the 1930s by the Indian-American astrophysicist Subrahmanyan Chandrasekhar. He derived it as a young man on a steamship voyage from India to England, and it now bears his name, the Chandrasekhar limit. When a white dwarf reaches this threshold, it collapses. A runaway thermonuclear fusion reaction rips through the entire star in a matter of seconds. The result is an explosion of extraordinary violence and brilliance, a supernova so luminous it can briefly outshine the entire galaxy in which it resides. Because these explosions always occur at essentially the same mass, the Chandrasekhar limit, they always produce essentially the same intrinsic brightness. They are, in the language of astronomers, standard candles. And a standard candle is a cosmologist's dream, because if you know how bright something actually is, you can measure how bright it appears from Earth, and calculate its distance precisely. The dimmer it looks compared to how bright it should be, the further away it is. Type Ia supernovae are bright enough to see at distances of billions of light-years. That means they can be used to measure cosmic distances on scales reaching deep into the history of the universe, back to times when the universe was a fraction of its current age. And in the mid-1990s, two independent teams of astronomers decided to exploit exactly this capability. The first team was the Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory, and led by the physicist Sol Perlmutter. The second was the High Z Supernova Search Team, led by the Australian astronomer Brian Schmidt, with a young Harvard-trained researcher named Adam Rees playing a key analytical role. Both teams were hunting distant Type 1a supernovae, measuring their brightness carefully, calculating their distances, and comparing those distances to how fast their host galaxies were receding from us. The goal was to map the expansion history of the universe, to see how quickly it had been expanding at different points in cosmic time, and from that, to determine the deceleration rate due to gravity. Both teams expected deceleration. The whole point of the exercise was to measure by how much. The results began coming in through 1997 and into 1998, and they were bewildering. The distant supernovae were dimmer than expected, not by a tiny amount, by a clearly significant amount, and dimmer meant further away than they should have been, given the recession speeds of their host galaxies. The only consistent explanation, the explanation that both teams converged on independently, despite checking the data repeatedly for errors, was that the expansion of the universe was not decelerating, it was accelerating. Distant galaxies were not being slowed by gravity. They were being driven apart faster and faster by something that gravity could not account for, something that was, in effect, working against gravity, something with a repulsive influence spread throughout space itself. Both teams looked hard for alternative explanations. Could the supernovae be dimmed by dust in the intervening space? Careful analysis of the spectral signatures showed this was not a sufficient explanation. Could the supernovae themselves be intrinsically different at earlier cosmic epochs, producing less light than their modern counterparts? Extensive study of their spectra and light curves showed no evidence for such evolution. Could there be systematic errors in the calibration methods? Both teams had used different approaches and reached the same conclusion. The acceleration was real, and both teams published their results in 1998 and 1999, announcing to the world something that almost nobody had predicted. The expansion of the universe is speeding up. The universe is not coasting to a gentle halt. It is racing apart, and the racing is getting faster. The unknown cause of this acceleration was given a name: dark energy. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics. The Nobel Committee described the discovery as the most surprising and consequential observation in cosmology since Hubble, and it was, because now the cosmological constant that Einstein had once called his greatest blunder was back on the table, not as an error to be corrected, as a possible description of something real. Here is where things get philosophically deep, and in places genuinely uncomfortable for physicists. We've detected something real. We've measured its effects. We've mapped its influence across billions of years of cosmic history. But we don't know what it is. We've given it a name, but a name is not an explanation. So let's walk through the major ideas, because they are each fascinating in their own right, and each carries its own profound implications. The simplest and most mathematically natural explanation is that dark energy is precisely what Einstein's discarded cosmological constant represented: a fixed, uniform energy density inherent to empty space. Not matter, not radiation, not a field carried by particles, just space itself, having energy. Every cubic meter of empty space, everywhere in the universe, at all times, containing a small but tungo amount of energy. This energy would exert a negative pressure, a repulsive effect, that drives space apart. Think for a moment about what it means for empty space to have energy. Imagine the most perfect vacuum imaginable. Every particle removed, every photon of light absent, absolute nothingness, to every classical definition of the word. Now imagine that this nothingness is not truly nothing, that it hums with a faint but real energy. That emptiness has a cost, a value, a substance. That's what the cosmological constant proposes. And in the framework of quantum mechanics, this is not as bizarre as it sounds. Quantum field theory, the most precisely tested physical theory in human history, tells us that a true vacuum is not truly empty. At the quantum level, empty space seethes with activity. Virtual particles constantly flicker into and out of existence, borrowing energy from the vacuum for moments too brief to violate the uncertainty principle before annihilating back into nothing. This constant quantum activity contributes a real energy to the vacuum. It's called zero-point energy, and it is a genuine, measured prediction of quantum mechanics. So the vacuum energy is real. It exists. The cosmological constant could naturally be identified with it. Problem solved, right? Not even slightly. Here is the problem, and it is one of the most dramatic and humiliating problems in all of physics. When you actually calculate how much vacuum energy quantum field theory predicts, when you add up all the contributions from all the quantum fields we know about, you get a number, and that number, compared to the dark energy density we actually observe in the universe, is wrong. Not slightly wrong, not off by a factor of 2 or 10, off by a factor that, depending on how you do the calculation and where you set the cutoff, is somewhere between 10 to the power of 120. Try to feel the weight of that for a moment. 10 to the power of 120 is a number so large it makes the number of atoms in the observable universe look like a rounding error. The theoretical prediction and the observed value are separated by more than 100 orders of magnitude. It is, without exaggeration, the worst quantitative prediction in the history of science. Physicists call it the vacuum catastrophe, or sometimes just the cosmological constant problem. And it is not a small technical difficulty awaiting a small technical fix. It is a screaming signal that something fundamental is missing from our understanding of how quantum mechanics and gravity fit together. Something, somehow, cancels out almost all of that vacuum energy. Some mechanism, unknown, reduces the effective cosmological constant from its theoretically monstrous value to the tiny but tungo value we observe. The cancellation is so precise, leaving behind exactly the right amount to drive cosmic acceleration, that it requires either a profound physical mechanism we haven't discovered, or a fine-tuning of parameters so extraordinary that many physicists find it philosophically untenable. This discomfort with fine-tuning has motivated the second major category of dark energy explanations, quintessence. The word itself has a history. It comes from the ancient Greek and Latin term for a fifth element, the ethereal celestial substance the ancient philosophers believed filled the heavens beyond the realm of earth, water, fire, and air. In modern physics, quintessence refers to a hypothetical dynamic field that permeates all of space, similar in some ways to other fundamental fields, like the electromagnetic field, but with distinctive properties designed specifically to explain cosmic acceleration. The key difference between quintessence and the cosmological constant is dynamism. The cosmological constant is fixed. It is the same everywhere, at all times throughout the history of the universe. Quintessence, by contrast, would evolve. Its energy density could change over time. Its influence on cosmic expansion would vary, depending on where the field sits in its potential energy landscape. A concept similar to the way a ball rolling down a hill has different amounts of energy depending on its position. Some quintessence models predict that the effective dark energy density could have been different in the early universe, different today, and different again in the far future. The appeal of quintessence is that a dynamical field might evolve naturally toward a small value today without requiring absurd fine-tuning. Some models are designed so that the field's energy density tracks other components of the universe, matter and radiation, keeping pace with them through cosmic history, and only beginning to dominate recently. These are called tracker models. They attempt to explain not just that dark energy has a small value, but why it has approximately the same magnitude as the matter density today, when the universe is about 13.8 billion years old. This near coincidence, often called the coincidence problem, is another puzzle that standard cosmological constant explanations struggle with. The challenge for quintessence models is observational. We haven't detected the field directly, and distinguishing between a true cosmological constant and a slowly evolving quintessence field requires measuring subtle changes in the expansion rate over very long cosmic timescales, measurements that push current observational technology to its limits. What scientists look for is a quantity called the equation of state of dark energy, usually denoted by the letter W. For a pure cosmological constant, W equals exactly -1. For quintessence models, W can be different from -1 and might vary with time. Current observations are consistent with W being close to -1, but they are not yet precise enough to rule out dynamical alternatives. There are even more radical proposals. Some physicists suggest the problem lies not with a new form of energy, but with our theory of gravity itself. Perhaps general relativity, extraordinarily successful on the scales we've tested it, from millimeter laboratory experiments all the way to binary pulsars, and the detection of gravitational waves, breaks down or behaves differently when applied to the universe on its largest scales. These modified gravity theories attempt to explain cosmic acceleration as a purely geometric effect, not an energy pushing space apart, but a failure of Einstein's equations when the curvature of spacetime is very small, as it is on cosmological scales. Some modified gravity theories, such as FFR gravity, replace the simple curvature term in Einstein's equations with a more complex function. Others, like DGP gravity, named for its developers Gia Dvali, Gregory Garbadadze, and Massimo Porati, introduce extra spatial dimensions that become relevant at large distances, leaking gravity into a higher dimensional bulk and modifying cosmic expansion in ways that can mimic dark energy. These ideas are mathematically sophisticated and observationally constrained, but none has yet emerged as a clearly superior alternative to the cosmological constant. And then there are the most radical ideas of all, touching the edges of what current physics can even address. Some proposals connected to string theory suggest that the vacuum energy we observe is just one of an astronomically large number of possible values, a vast landscape of possible universes, each with its own vacuum energy. In a multiverse where all these possibilities are realized somewhere, we simply find ourselves in a region with a small but positive cosmological constant, because only in such regions can galaxies, stars, and life form. This is called the anthropic argument, and it is deeply controversial. Many physicists find it profoundly unsatisfying, because it seems to surrender the ambition of deriving dark energy from first principles. It explains by pointing to our own existence, rather than to a mechanism. But others regard it as genuinely illuminating, a recognition that the values of physical constants may not be uniquely determined by any deeper theory, but selected from among many possibilities by the conditions required for observers to exist. The honest state of play, as physics stands today, is this: we do not know what dark energy is. Every leading explanation carries unresolved difficulties. None has achieved consensus. The cosmological constant fits the data beautifully, but the vacuum catastrophe makes its theoretical foundation deeply problematic. Quintessence is theoretically motivated, but undetected and unconstrained. Modified gravity is creative and testable, but no version has convincingly outperformed the standard model. The mystery remains open, You might be wondering how science studies something that can't be seen, touched, or detected by any instrument directly. Dark energy leaves no tracks in a particle detector. It doesn't emit radiation. You can't bottle it. You can't weigh it. So how do astronomers and physicists actually investigate it? The answer is that we study its effects with extraordinary precision. We measure the history of cosmic expansion, the large-scale structure of the universe, and the subtle distortions in light traveling across billions of light-years of space. From those measurements, we work backward to determine what must be causing what we observe. It is, in a sense, forensic cosmology. The first and most important method is the cosmic distance ladder. Think of the problem of distance measurement in space as a series of nested techniques, each one calibrated using the one below it, each one reaching further into the universe than the last. At the base of the ladder are the nearest stars, whose distances we measure using parallax. The principle of parallax is something you can demonstrate with your own hand. Hold a finger up in front of your face and close one eye. Note where your finger appears to be against the background. Now switch eyes. Your finger appears to jump against the background, because you're viewing it from a slightly different angle. The amount of that apparent shift tells you how far away your finger is. Astronomers do the same thing with nearby stars, using the diameter of the Earth's orbit as a baseline. Observing the same star 6 months apart, when the Earth is on opposite sides of the Sun, and measuring how much the star appears to shift against the far more distant background stars. This technique works for stars up to a few thousand light-years away. From parallax-calibrated stars, we move up to a class of stars called Cepheid variables. Cepheids are stars that pulsate. They rhythmically expand and contract, brightening and dimming with a very regular period. And here is what makes them so valuable. A Cepheid's period of pulsation is directly related to its intrinsic luminosity. The slower it pulsates, the more intrinsically luminous it is. This relationship, the period-luminosity relation, was discovered by a remarkable astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 20th century. Leavitt was employed as a human computer, part of a group of women hired to process photographic plates of the sky and catalogue stellar brightnesses. For much of her career, she held the title of computer rather than astronomer, and was paid 25 cents per hour. But her meticulous work cataloguing Cepheid variables in the Magellanic Clouds, 2 small galaxies orbiting the Milky Way, led her to notice the period-luminosity relationship in 1908, because the stars in the Magellanic Clouds are all at roughly the same distance from Earth. Any variation in their apparent brightness reflects real differences in their intrinsic brightness. Leavitt found that the brighter Cepheids pulsated more slowly, and she quantified the relationship precisely. It was this tool that Edwin Hubble later used to measure the distances to nearby galaxies and confirm the expansion of the universe. Without Henrietta Leavitt's work, modern cosmology would look very different. She died in 1921, before the full implications of her discovery were understood, and was therefore ineligible for the Nobel Prize that many felt her work deserved. Cepheids extend our distance measurements to tens of millions of light-years. From there we move up to Type 1a supernovae, whose standard candle properties, as we've already explored, extend our reach to billions of light-years, deep into cosmic history. But supernovae are not the only cosmological tool. A second powerful technique involves something called baryon acoustic oscillations, and it requires a little setup to appreciate properly. In the early universe, in the first few 100,000 years after the Big Bang, the cosmos was an extraordinarily hot, dense plasma. Electrons, protons, and photons were so energetically coupled together that they behaved as a single fluid. Through this fluid, pressure waves propagated, essentially sound waves, carrying energy outward from dense regions. These waves had a characteristic scale determined by how far a sound wave could travel in the time available before the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. That transition, called recombination, happened about 380,000 years after the Big Bang. At that moment, the plasma became transparent, the coupling between matter and light ended, and the pressure waves were frozen in place, like ripples suddenly locked into ice. The scale of those frozen ripples, approximately 490 million light-years in today's expanded universe, left a permanent imprint on the distribution of matter. Galaxies today have a slight preference for clustering at separations close to this characteristic scale, because the regions of slightly enhanced density at the peaks of those ancient sound waves were the seeds from which galaxies preferentially grew. By measuring this characteristic clustering scale in surveys of millions of galaxies at different distances, different look-back times, astronomers can see how the universe has expanded between different cosmic epochs, and from that expansion history, they can infer the influence of dark energy over time. It is like using the frozen sound waves of the early universe as a cosmic ruler, a standard length scale that can be measured at different points in cosmic history to track how space has stretched between them. A third major technique is weak gravitational lensing. Einstein's general relativity predicts that any mass curves the spacetime around it, and that light traveling through curved spacetime follows curved paths. This gravitational lensing effect is most dramatic and obvious when light passes very close to a massive object, a galaxy cluster for instance, and is bent into arcs or rings. But even the diffuse distribution of matter spread throughout the universe causes subtle coherent distortions in the shapes of distant galaxies. Images of distant galaxies are slightly stretched and sheared by the gravitational influence of all the matter lying between them and us. This effect is too small to detect in any individual galaxy, but it becomes measurable when you analyze the shapes of millions or billions of galaxies statistically. The pattern of distortions reveals the distribution of mass in the intervening space, and because dark energy affects how fast structure, the cosmic web of filaments and voids, grows over time, the lensing signal carries information about dark energy's behavior across cosmic history. These three techniques, standard candles, baryon acoustic oscillations, and weak gravitational lensing, are complemented by detailed analysis of the cosmic microwave background. The CMB, as it is known, is the earliest light we can observe, radiation emitted when the universe first became transparent, 380,000 years after the Big Bang, now cooled by the universe's expansion to a temperature of just 2.7 degrees above absolute zero. Its tiny temperature variations across the sky, fluctuations of about 1 part in 100,000, encode an extraordinary amount of information about the composition, geometry, and early history of the universe. The precise pattern of those fluctuations is exquisitely sensitive to the amounts of dark matter, dark energy, and ordinary matter in the universe. By matching theoretical predictions to the observed CMB pattern, cosmologists can extract remarkably precise measurements of all these quantities. The combination of these independent methods, each with its own systematic uncertainties, each probing dark energy in a different way, gives us the current standard model of cosmology, often called lambda CDM, lambda for the cosmological constant, CDM for cold dark matter. It describes a universe that is approximately 68% dark energy, 27% dark matter, and 5% ordinary matter. It fits an enormous variety of observations with remarkable consistency, and new instruments are being deployed right now to test it with even greater precision. The Dark Energy Spectroscopic Instrument, or DESI, mounted on a telescope at the Kitt Peak National Observatory in Arizona, uses 5,000 robotic optical fibers to simultaneously measure the spectra of 5,000 galaxies at a time, mapping their recession speeds and distances with extraordinary precision. It is building a three-dimensional map of tens of millions of galaxies, tracing baryon acoustic oscillations across huge swaths of cosmic history. The Euclid satellite, launched by the European Space Agency in 2023, is mapping the shapes of billions of galaxies to measure weak gravitational lensing and baryon acoustic oscillations simultaneously across a third of the entire sky. The Vera C. Rubin Observatory, now coming online in the mountains of northern Chile, will image the entire visible southern sky repeatedly, building up a deep, detailed, time-resolved survey of billions of galaxies, and will detect hundreds of thousands of Type 1a supernovae over its 10-year mission. Together, these experiments are designed to measure the equation of state of dark energy, that critical parameter W, with enough precision to detect even a small deviation from -1. Any deviation would be a sign that dark energy is not a simple cosmological constant, but something richer and more dynamic, something we are even further from understanding, or perhaps a sign pointing toward the next revolution in physics. To really appreciate what dark energy means for the universe, it helps to zoom out and look at the grand structure of the cosmos, the enormous scaffolding of matter on which galaxies and clusters are arranged. Because dark energy doesn't just drive the overall expansion of space, it has profoundly shaped the structure of everything we see. Have you ever looked at a sponge? Not a synthetic one, but a natural sea sponge, with its irregular network of holes and channels and interconnected solid material. The large-scale structure of the universe looks something like that, but on scales that beggar imagination. Galaxies are not scattered randomly through space. They are arranged in a vast cosmic web, long filaments of matter, stretching hundreds of millions of light-years, sheets of galaxies at their intersections, dense clusters of hundreds or thousands of galaxies at the nodes where filaments meet, and enormous voids, regions hundreds of millions of light-years across containing almost no galaxies at all, filling the spaces between. This web didn't exist at the beginning. In the very early universe, matter was distributed almost perfectly uniformly. Almost, but not quite. Quantum fluctuations in the primordial plasma, tiny, random variations in density, were stretched to cosmic scales by a period of extraordinarily rapid expansion in the universe's first fraction of a second, an epoch called inflation. These tiny seeds of overdensity were the starting points for all the structure we see today. Over billions of years, gravity amplified them. Slightly denser regions attracted more matter, growing denser still, while slightly underdense regions lost matter to their surroundings, becoming voids. The filaments and sheets and clusters and voids emerged gradually, over cosmic time, from those nearly invisible initial seeds. And dark energy played a crucial role in shaping this process. In the early universe, dark energy was present but relatively unimportant. The universe was much smaller then, much denser, and ordinary matter and radiation dominated the energy budget. Gravity was strong, and structure grew vigorously. But as the universe expanded, matter spread out and its density fell. Dark energy, with its constant energy density per unit volume, became a progressively larger fraction of the total. About 5 to 6 billion years ago, dark energy became the dominant component of the universe's energy budget. And at around that time, expansion stopped decelerating and began accelerating. This transition from a matter-dominated universe where gravity was winning to a dark energy-dominated universe where expansion was taking over had real consequences for the formation of structure. In a matter-dominated universe, gravity can continue to pull matter together, forming new clusters and filaments indefinitely. But once dark energy takes over and expansion accelerates, the distances between galaxies and clusters grow faster than gravity can overcome. The growth of structure is suppressed. Existing structures, bound by their own internal gravity, are preserved, but new large-scale structure stops forming. The cosmic web is, in a sense, frozen at the configuration it had reached when dark energy began to dominate. This means that the cosmic web we observe today is a snapshot of structure formation at a particular moment in cosmic history, a moment determined by when dark energy took over. Understanding the detailed properties of the cosmic web, the masses and distributions of galaxy clusters, the statistics of voids, all carry information about dark energy and its history. They are all, in a sense, fossils of the competition between gravity and dark energy across cosmic time. There is something quietly profound about this. The arrangement of galaxies across the night sky, the pattern we would see if we could somehow step back and view the whole universe from outside, is not random. It is not simply the product of gravity acting alone. It bears the imprint of dark energy. The voids are partly dark energy's doing. The way growth stopped when it did, fixing the scale of the largest structures, is dark energy's signature. The universe looks the way it does because of something we still cannot fully explain. Now let's turn to the future. Because the nature of dark energy doesn't just tell us what the universe is made of today, it determines, quite literally, the ultimate fate of everything. Have you ever watched a river carry a leaf downstream? At first the leaf is close and visible, turning slowly in the current. Then it moves further away, harder to see, more distant. Eventually it rounds a bend or simply recedes too far, and it is gone from your view, not destroyed, just beyond reach. Something similar is happening to the galaxies of the universe, playing out over billions of years instead of minutes. As space accelerates in its expansion, galaxies beyond a certain distance are receding faster than light itself can travel toward us. Their light will never reach us. They have crossed what cosmologists call the cosmic event horizon. They are, for all practical purposes, gone from our observable universe. Right now, our observable universe contains roughly 2 trillion galaxies. In several billion years, as acceleration continues, galaxies near the edge of that horizon will begin crossing it and vanishing from view. In tens of billions of years, the local group, the small cluster of galaxies to which the Milky Way belongs, gravitationally bound together, will be an island in an increasingly dark and empty cosmos. Andromeda, which is currently on a collision course with the Milky Way and will merge with it in about 4 billion years to form a new giant elliptical galaxy, will be our nearest permanent neighbor. Everything else will recede into unreachable darkness. But the specific fate of the universe depends critically on what dark energy actually turns out to be. If dark energy is the cosmological constant, a fixed, unchanging vacuum energy, then the future of the universe is what cosmologists call the Big Freeze, or the heat death of the universe. Expansion continues indefinitely, accelerating gradually. The universe becomes ever emptier as everything beyond the local group recedes beyond the horizon. Over timescales of trillions of years, the remaining stars exhaust their fuel and burn out. The night sky, from any vantage point in the surviving galaxy, gradually dims and darkens as stars die and are not replaced. Stellar remnants, white dwarfs, neutron stars, slowly cool toward absolute zero. Black holes accumulate, dominating the mass of the galaxy. Then, over timescales of perhaps 10 to the power of 67 years or more, even black holes slowly evaporate through the process of Hawking radiation, a quantum effect predicted by Stephen Hawking in 1974, by which black holes gradually emit thermal radiation and lose mass until they completely disappear. Eventually, the universe approaches a state of maximum entropy, maximum disorder, minimum useful energy. No temperature gradients remain to drive any process. No work can be done. Time, in any meaningful sense, becomes an empty concept. The universe reaches a state of absolute eternal stillness. Now, if dark energy is not constant, if it is a dynamic field whose energy density increases over time, then a more dramatic and violent fate becomes possible. This scenario is called the Big Rip. Imagine dark energy growing stronger with time. At first, as today, it merely accelerates the expansion of the universe on the largest scales, but as dark energy's density increases, it eventually overcomes gravity on smaller and smaller scales. Galaxy clusters are pulled apart. Individual galaxies are shredded. Solar systems are dismembered. The gravitational bonds between stars and their planets snapped by the accelerating expansion of space. Then the expansion overcomes the electromagnetic forces holding planets and moons together, and they are pulled apart. Then molecules, then atoms, then in the final moments, which some models place at perhaps 20 to 50 billion years in the future, though with enormous uncertainty, the strong nuclear force holding atomic nuclei together is overwhelmed, and nuclei themselves are torn apart. Every bit of structure in the universe, at every scale, is destroyed simultaneously by the runaway expansion of space. The Big Rip is the most violent possible ending to the cosmos. There's also the possibility that dark energy could weaken over time, or change sign, becoming attractive rather than repulsive. If dark energy gradually diminishes and then reverses, expansion would halt and the universe would begin to contract, at first slowly, almost imperceptibly, then faster and faster. Galaxies would begin approaching each other. The night sky from any vantage point would begin to brighten. The cosmic microwave background would blue shift from cold microwaves toward infrared, then visible light, then ultraviolet. Temperatures everywhere would rise. Eventually galaxies would merge into a hot, dense cosmic soup. In the final moments, everything, all matter, all energy, all the complexity built up over the entire history of the universe, converges back to a single inconceivably hot and dense point, the Big Crunch. Some theoretical frameworks, particularly those inspired by certain interpretations of string theory and loop quantum cosmology, suggest that a Big Crunch could trigger a new Big Bang, that the universe exists in a perpetual cycle of expansion and contraction, with no ultimate beginning or ending, just an eternal rhythm of cosmic birth and collapse. These are not metaphors, they are genuine predictions of physical theories, each tied to specific possible values of dark energy's properties. The universe has one fate. We don't yet know which one. The answer is written into the nature of dark energy, and we are, right now, building the instruments to read it. As we come to the end of our journey tonight, it's worth sitting quietly with what we've covered. We live in a universe that is 95% unknown, that is not a failure of science. It is science doing its deepest work, mapping the boundaries of the known, and illuminating how vast the unknown remains. Dark energy is the largest single ingredient in the universe, and we cannot say with certainty what it is. We can say what it does. It fills space. It drives expansion. It has been reshaping the cosmos for billions of years. We can say how it was discovered, through the painstaking measurement of dying stars at the edge of the visible universe, by researchers who expected to find something completely different. We can say how we study it, through supernovae, through the frozen sound waves of the ancient plasma, through the bent light of a billion galaxies. And we can say what it implies, a universe growing ever larger, ever emptier, heading toward one of several possible endings, all of them extraordinary. Think about the fact that Einstein inserted the cosmological constant into his equations to avoid a prediction he didn't believe, then removed it as his biggest blunder, and that the universe then turned out to require something very much like it after all. Think about Henrietta Leavitt, cataloguing stars for 25 cents an hour, laying the groundwork for the measurement of the expanding universe without ever being given the title of astronomer. Think about Adam Rees staying up late in the late 1990s analyzing supernova data, seeing numbers that didn't make sense, checking and rechecking until the impossible became undeniable. Science is full of these moments, human beings pressing against the edge of knowledge until something gives. The cosmological constant problem, that monstrous mismatch between quantum mechanics and what we observe, may be one of the most important open doors in all of physics. It is pointing at something. It is insisting that our understanding is incomplete in a specific, measurable, deeply significant way. The next great theory of physics, whatever unifies quantum mechanics and general relativity, whatever explains the nature of space at its deepest level, will almost certainly have to resolve this problem. And when it does, it will probably transform our understanding of dark energy in the process. Right now, new telescopes are gathering light. New surveys are cataloguing millions of galaxies. New measurements of the equation of state of dark energy are being made. The universe is out there, doing what it has always done, expanding, evolving, carrying its galaxies apart across deepening distances, indifferent to whether we understand it. And we, this remarkable, restless, 5% species, keep looking up and asking questions. There is a particular feeling that comes from genuinely reckoning with the scale of what we don't know. Not anxiety, or at least not only anxiety, something closer to vertigo. And then, if you stay with it long enough, something that opens into wonder. We are made of the 5%. We are the atoms and the molecules and the neural connections, the warm and temporary arrangement of ordinary matter, looking out at the 95. We are asking the universe what it is made of, and the universe is telling us, slowly, that it is mostly made of things it has not yet fully revealed. And still, the stars are out there, and the space between them hums with something we have not yet learned to name. That is where we leave it tonight.